All right, so we're going to continue looking at SAS Activity 4 today, which you can find under Weekly Content, Week 10 Non-Parametric Test. Okay. So as a reminder, we are looking at this Monty Hall activity as it's related to the Wilcoxon rank sum test. Specifically, we're going to be using the Wilcoxon rank sum test to answer or help us decide what's the better decision to stay or switch our door when we're in this scenario where we selected a door among 3 to start. We don't know what's behind any of them, but we always get shown one door not being the one we selected as having a goat, the loser, essentially one of the 2 losers, and then we have the option to stay or switch. As a reminder, this classic question of what's the chance of winning if you stay or switch is known as the Monty Hall problem. And it was a difficult problem for people to figure out initially, especially without computer simulations, although now it's fairly straightforward to answer this problem, to simulate it, say 1 million times, and you get a very definitive answer. But so we played using the applet, right? So you could click here, and you could even have it do 10 times and say, oh yeah, let's say I stay, and then it shows you how many times you win, simulates the game 10 times. So like in this case, I won twice out of 10. It's not very good, right? Staying. And everyone did that and then recorded via this Google form how many times they won out of 10. Like half the class stayed, half the class switched. Okay. So we have this data in SAS Studio. So let's get SAS Studio open back up. And actually, last time I had trouble updating the data, so we were using data from a previous semester, but now it's in the same file, so we don't need to change the code, but it's actually updated, so now it's reflective of your responses, what you did last class. So let's see. So we had imported the data, printed it, and then conducted some exploratory data analysis using proc-sgplot and proc-means. So let's just run our whole SAS script and see where we're all at. So I think there was 20 responses total. Here's like the first 10. So the number of times someone won out of 10, and then whether they stayed or switched, right? And here is the box plots. Okay, so already looks like a pretty clear indication that it's maybe not 50-50. All right. So looking like switch is better here, right? You win more often, it looks like, typically. And if we look at the means, so yeah, we had 20 people, 7 and 13, so very small sample sizes. Certainly people win more on average when they were switching versus staying, right? Okay. But a sample size of 20 doesn't like prove anything definitively. Just seems to be trending that way. So we can use a t-test to get a more rigorous answer, I suppose. But as a reminder, the t-test relies on some assumptions for each group. Specifically, we need a random sample overall, which actually is pretty reasonable here, given that we used the applet. But then also normality for each group, okay, for the 2-sample t-test. So that's where normality might be a little questionable here. So let's see exactly which part we ran. Okay, 1C. And I updated the SAS document a little bit to make clear that this is not like a regular activity where we type in here everything we're going to be doing in the SAS program itself. So when we type responses, we'll do it in the SAS comments. Okay. All right, so we've gotten through 1C. Oops. Anybody have any questions? Or let's try and run your code through 1C and make sure that runs okay before we keep moving on to the next part here. Anybody have any issues with the SAS code? I know sometimes an error pops up even though it was like running okay last time. So it looks like we're doing okay. I see some box plots and stuff. Okay. Cool. Then let's see. Let's get rid of that. Like I didn't do that yet. So 2A, we were looking at using a 2-sample t-test, and we wanted to check the assumptions, right? So it's been a bit since we looked at the 2-sample t-test, right? So probably pulling up the guide for Stat 216 document is a good thing, which it's always linked to under the course schedule here. Okay. So let's look at the 2-sample t-test and remind ourselves of the assumptions here. So we had normality and independence. Okay. So we'll call it like assumption 1 and assumption 2. A lot of people just use the t-test in general and don't really do the best job of checking assumptions, right? So this is like the important step. I think it's quite easy given software nowadays for anyone to run a t-test. The tricky part is being able to check the assumptions correctly. Because unfortunately, right, if the assumptions are not met, the results are not valid. So like the software gives you numbers, but we can't really rely on them. So this is an important step always. So normality here, which I copied from this part of the guide document. And let's make that a little bigger. Oops, too big. There we go. Okay, so for normality here, if you looked at the results, all right, let's do this. Okay. And I think I added this normal option here, which we did not have last time. So we add the normal option that also gives the hypothesis tests of normality. Which again, I know it's been a bit. Does anyone remember how we feel about those as tools for checking normality? Probably prefer QQ plots, yeah. These hypothesis tests of normality, the issues with them as a reminder is if your sample size is like bigger than 20, it'll always say the data is not normal, pretty much, even if the data is truly generated from a normal distribution. So if the sample size is too big, they're not reliable. Conversely, if they're too small, they also always say it's not normal. So it has to be in this like Goldilocks zone, like just right sample size, typically like 10 to 20, I think. is the only time they're somewhat reliable, which is our case here. We have 713 for the sample sizes, so we can use it as just like an assurance after looking at the plots as well. But I wouldn't rely on them alone. So looking at, we get like two sets of results because we have two groups, one for the stay and one for the switch. So looking at stay first. Okay. Here's like the histogram. It's like flipped horizontally. How is the histogram looking? Not very bell-shaped, no. That's pretty awful, actually. But the QQ plot, actually, how does the QQ plot look? Yeah, that's actually not bad. In fact, this is like, I'm surprised at how good this looks. Like the points, there's always some randomness in the points around the line, but as a reminder, if we look like the guide document, I give examples of what QQ plots look like when it's truly normal or not. Okay, here's one where it's like truly normal. So you get some like curviness around that diagonal line. It doesn't have to fall in there perfectly. And that's normal. So that's pretty similar to this case here. Like it looks pretty good, actually. So let's see. Yeah, no, from the box plot, an important thing to tell is that there's no outliers. And also, actually, how does it look in terms of symmetry based on the box plot? Like it's really good. The mean and median are pretty much equal. Again, surprising. But, well, not pretty much equal. Apparently in our sample, they are exactly equal. So this, it's very symmetric. So summarizing that. Okay, yeah, a few things to note. So the histogram somewhat problematic in that it is not bell-shaped, but the box plot shows a symmetric distribution. Okay. With no outliers. And the points on the QQ plot do not stray far from the diagonal line. Overall, normality appears to be met for, let's see, which group was that? Switch? Oh, that was stay. For the stay group. Okay. So a sample size of 13 normally would make us a little nervous, but because there's no outliers and it's symmetric, for the t-test, that's actually like, this is perfectly fine. Like the t-test results would be very reliable in general. Practically speaking, like the symmetry is a huge influence over whether the results of the t-test are valid long-term when your sample size is small. Okay, so this looks really good actually for the first group, but as a reminder for the two sample t-test, we need it met for both groups in order for the assumption to be met overall. So for the second group, for the switch group, let's see. So our sample size is 7. That's not great. That's really small. In fact, when you have a sample size of 7, it's almost hard to justify in any case that it's normal, because there's just not even enough points to get a good grasp of like the distribution. But we can see, looking at the histogram, again, that doesn't look great. And the box plot is not there to bail it out this time. Like the box plot does not look symmetric. It doesn't even draw the line for the median. That's why didn't SAS do that for us? There is a median. Oh, it's the same again. Or wait, no, it's not. It's just similar. Okay. Mean and median are similar, but yeah, the distribution doesn't look great there. And then looking at the QQ plot, how does the QQ plot look this time? Like this is not great. Yeah, we have this like sort of like bend, like this curved shape, which if you see in the examples, it's almost kind of like this one. Yeah.
It's almost like not pulled out, but the median is the same as the map. Like that top blue line.
Oh, is that why it's covering up? Oh, okay. Yeah, thanks. Interesting. Yeah. Also probably not good for normality if the median is equal to the maximum. Yeah. No, it's not good. Okay, interesting. I don't think I've ever seen that for a data set before. It's just because it's so small. So yeah, it's like not looking great here. We have this, right, is okay. It's like this curve here. When you see this in the QQ plot, which is kind of like what we have going on here, it's a little bit of this like downward curve like this. That's indicating the distribution is left skewed. Okay. So, which makes sense because the mean is less than the median, which corresponds to it being left skewed here as well. Okay. So yeah, overall, not great. It's problematic to say the least. So let's copy this. Histogram is problematic. Okay, yeah, let's say like for the stay group. Oops. And the other one's for the switch group. Histogram is problematic. And the box plot shows an asymmetric distribution. SAS doesn't say there's any outliers because it would use like symbols to show if there was outliers, but and the points on the QQ plot do stray far from the diagonal line. So overall, normality appears to just essentially negating a lot of the things that we said for the previous group. Okay. So normality not for the second group, but it looked great for the first group. So overall, what does that mean for our 2-sample t-test? So it met for one group really well, not for the other group. That means overall, we could, technically, if either group has it violated, then the overall assumption is not met. So since normality assumption not met for both groups, yeah. Oh yeah. Yeah, that's They'll stop doing that. Yeah. Did that work? No? Um, any questions about how we check those assumptions for the two sample t-tests? Or like why it's violated? It's also the case if you have a response that's a whole number like this, like number of times 1 out of 10, technically the t-test wants a continuous response variable, whereas this is discrete. So that's sort of another knock on the assumptions being met. In general, if your sample size is big, you can still use the t-test when you have a discrete response variable, but it's like the combination of the sample size being small here, a discrete quantitative variable, not bell-shaped distributions. There's just a lot of things that are problematic here. So not met. Was that working now for the typing? Oh no. Shoot. Okay, so our assumptions appear to be met. No. Okay, so that was 2A. Now for 2B, we're gonna just go ahead with the t-test because we're feeling like we're gonna get crazy today, I guess. Do it anyways, even though the assumption's not met. So t-test, these are aptly named proc t-test. Data equals Monty Hall. And we actually specify the response variable using a var statement, just like we did in proc univariate, and the grouping variable determining the two groups using a class statement. Just like that. Okay. And I wanted to show today too. So has anyone used Chat GPT? I assume some people have in this class already, right? Okay, yeah. So it's really good for coding quite a bit. So it's free if you make an account. You can go here. And so for example, wanted to show like, let's say I didn't remember how to do the t-test in SAS. So I could Google it. But you can also like for Chat GPT, it works decently well with like, say something like write SAS code to implement a two sample t-test something like that. If you were trying to figure out how to do something new in SAS, like maybe especially something we didn't cover in this class, right? And then this works pretty well. Okay, so yeah, it's making a fake data set. 2 fake data sets, one. Okay. Well, that's interesting. I don't know if that syntax would work. It's kind of nice because it explains the parts too. So I found it's not the best at SAS code, but it's usually a good starting point. And you know, I wonder if that works. These fake data sets that it's making, those look good. I think that will work. Yeah, that worked. I made the fake data sets. And then let's see if their t-test works. I'm a little skeptical of that code. Yeah, okay. That didn't work. Oh, you got it wrong, ChatGPT. Anyway.
You can tell it that I don't try to fix it. Yeah.
Oh, that's true. Yeah, I should have. Yeah, I know. It's always very quick to admit it's wrong, isn't it? Yeah, like that is incorrect. Could you give? Oh no. That. Yeah, it's really good. Let's see if it gets it right this time. Okay, this looks better. See, you need like, yeah, the 2 variables in the same data set. There. Good job. Good job, ChatGPT. You got it on the second try. Okay, I think this looks correct now. So anyway, that could be a lot faster, especially with SAS. I found personally, I think SAS is really hard. Like there's not as much good online documentation for Googling things as other programming languages. So honestly, when I reviewed stuff for this class, yeah, there you go. Oh, there you go. It did it. Look, it did a valid t-test. So yeah, that was probably, I feel like, a little faster than Googling it, maybe. So anyway, that's a useful tool. Like, you know, of course, it's not good to plagiarize papers or anything, but I think if you can get accustomed to using it to help you like write code faster, it just makes you more efficient and spend less time Googling things. It's kind of like fancy Google, right? Yeah, for sure. Yeah. It's really cool. So
What's wrong?
yeah, the pieces. That's really, yeah, that's just super cool. Yeah, I wish this was around when I was in school and learning code, but at least it's around now. So yeah, sometimes it makes mistakes like that first time, but for the most part, it's pretty good. Okay. Okay, so we did it the old-fashioned way, and we typed it out ourselves. So here's the 2 sample t-test. Okay, we'll give formal statements of hypotheses, state our conclusions, give evidence to support our answers. So let's go back to the guide for Stat 216 document. Wonder how well this will paste into SAS. Probably not super great, but let's give it a whirl. So oh, it does paste the symbols. Okay, cool. So we'll say, and yeah, I just copied this from the guide for Stat 216 document. So we'll say our hypotheses are given by this, where mu1 is the average. And so what's our Let's look at which one's group one. Okay, so stay is group one. So what is mu1 in that case? Are they both what? Sorry. Yeah, exactly. The average number of times 1 out of 10, right? For, what did we say it was? Staying. Okay, staying is group one. And group two is the for switching. So I figured out which one like SAS decided was group one by looking at which group is listed first. That matters because the order of subtraction in SAS is group one minus group two. So since it's negative, that means group two was bigger, right? In terms of its average, which we can see from here too, but. All right, so that's our hypotheses. I asked for a lot here, very demanding. So, okay, also conclusions. All right, so conclusion. Let's give our test statistic. Which is a T for this test. So from here, what is our T test statistic for the uncooled T-test? Yep, yeah, exactly. Right here. That, and then our p-value is SAS's famous less than 0.0001. Yeah. SAS doesn't care if it's smaller than that. They're all the same. So what's our decision? Yeah, reject the null. Which, as a reminder, this whole thing is not valid because the assumptions were not met, but we're proceeding as if they were met. So then we would say, like, and then what would we say here? Or I guess which group is like describing which group is bigger, staying or switching here. Yeah, so is blank or switching, as opposed to staying. And then is it greater or less than? Greater, yeah. Yeah, so a really tricky thing in statistics is like we have confidence intervals, which we interpret as being 95% confident about, and then we have hypothesis tests, which are at the 5% significance level. So the thing, we interpret them differently, in part just because of like, that's the convention in statistics, to talk about confidence for confidence intervals and significance levels for hypothesis tests. But saying like testing at the 5% significance level is slightly different than 95% confidence. Because what this is saying essentially is because we say we have evidence, we're saying that the p-value is less than 0.05. But it could actually be like much smaller. So one way to think about it is we're actually like much more confident than 95% that the groups are actually different. But we still don't word it as like we're 99.99% confident. And that I think is just because of like convention in statistics. Like a lot of statistics is like giving the hypotheses this way because that's what people have done. Right, so there's a little bit of a distinction there that, again, is somewhat due to just because that's the way it's been done, which is kind of silly in a way. Okay, so we gave the results of the t-test. Okay, so on the Wilcoxon rank sum test now. Okay, so the Wilcoxon rank sum test, which actually in the guide documents, even though we're not going to have a homework over this, and it won't be covered on any exam, so maybe I just lost everybody right there. Everyone just checked out, like, oh, okay, I'm not listening. I still have this section in the guide document talking about how it works. It's very similar to the t-test, but instead of comparing averages or means between the groups, you're comparing medians. Okay. This is for a few reasons. I guess one way to think about it is like the point of using a non-parametric test like this is when assumptions are problematic for the first test, and the median, as a reminder, is like more robust to outliers. So if you have problems in your data set, testing about the median, maybe, the general idea is maybe that will go a little bit better than testing about the mean, which is very sensitive to outliers. Okay. It's also just based on different theory, but yeah, we give the hypotheses in a very similar way, but instead of saying the average, we just say median. Let's see what I asked for. Okay, checking with assumptions for 2C. So we will check assumptions for the Wilcoxon rank sum test. I think there's some pretty big limitations to it in that you still need these other assumptions, like normality is no longer a requirement. But I feel like their assumptions, in my opinion, are still quite strict and often not met. Which is also why we're kind of just glossing over this test in class, because in my opinion, it's a little bit not the most useful, because it's great if normality is not met that you have this as an option to consider now, but I feel like when normality is not met, it's not often the case that these assumptions would be met either. So, but we'll check it anyways here. So We need a random sample, so we can assume that's met here. The Wilcoxon-Rank sum test is good. It does not need a continuous quantitative response variable. It just needs it to be at least ordinal, actually. In this case, we have a discrete quantitative variable, so that's met here. Okay. So the first two assumptions are met for the Wilcoxon-Rank sum test. But we also need this similar shape and spread of the distribution of response values. And that's what, in my opinion, is a very strict assumption. Because it's not saying they need to be bell-shaped, but it's saying they need to have the same shape in both groups and the same amount of variability. Okay. So you could have like, see how well I can draw here. You could have like a histogram for group 1. That's like multimodal like this, right? And then it's like, oh, that's very abnormal. But if the second group like also has that weird shape, then the Wilcoxon-Rank sum test is valid. It seems like, to me, it's like a very specific, it's like, okay, how often is that true that you have this issue with normality and then the shapes of the groups are both the same? But I suppose it's better than nothing because the t-test is no longer valid here anyways. Okay. But that's the idea. They need to have the same shape if we look at like the histograms of both groups and also the same spread. And essentially they can just be shifted. Like that same distribution or same shape can be in a different spot for each of the groups, but needs to be roughly the same shape. So here, if we look at the plots again, this is where we can compare the shapes of the groups and looking at the histograms. So again, it's okay if they're shifted like horizontally. They don't, we're comparing the middle of the distributions. So that's okay to do this test if they're not lined up, but we need the same shape to have been in both spots. Does that look like it's the case here? Not really. No, this one's like, looks like it's right skewed, and this one looks like it's left skewed. So, yep. And again, yeah, this is the real data. This is from this class. So unfortunately, we're not going to see when assumptions are met here, I guess. But if they had both been right skewed in a similar way, then the assumptions would have been met. But so we'll say one group is right skewed and the other is left skewed. So the shapes are not the same, which violates the model assumption. Okay. What about the spread? So there's like a few different measures of spread you can look at. You can look at the range of the distributions and compare those to each other. the IQR. Does anyone remember how we can tell the IQR from these plots here? Right, the length of each box. And so looking at the range and the IQR here, how does the variability look between the two groups? Does it look similar? No, that's actually not similar either. This is what I'm getting at with like, okay, it's really hard for these assumptions to be met for real data where you have like normality being a problem. I feel like it's hardly ever met. So because the range, like here, this range is so much bigger for the state group than the switch group. Same with the IQR. The IQR is a lot bigger. Looks like it's about twice as big. So nope. So the variability is not similar. Okay. The reason these assumptions are necessary is because the way this test is constructed is essentially the person who constructed the test based it under this idea that the distributions are exactly the same except for a shift in just position, in like horizontal position here. And so that's how they can test for a difference in the median in that way. But it relies on the assumption of they're exactly the same except for where the middle is at. And so that's just not true here. So technically, Wilcoxon rank sum test is not valid here, but we will proceed for the sake of the problem. Okay. And yeah, showing ChatGPT. I tried this before class, and I feel like it did a pretty good job. So, like, I'll show how to write the code, of course, but I feel like it does a pretty good job of that too, I'm guessing. Maybe we'll let that. Oh, there you go. Oh, it's enthusiastic. It's fun. Okay, that's good. It did the two variables, one for the group, one for the value. So it's like making fake data here to run the test on. Okay, we don't need that many values. All right. Hey, it's doing it. That's correct. Okay. So great. That, yeah, in my opinion, that's much faster than Googling it. So like, we'll just let it keep talking to itself there. So it's very similar to the setup of the t-test. You'll note that we have this var statement to say like, what's the response variable? And this class statement to say, what's the grouping variable? Okay. It's the same way here. And actually, it gives it in the opposite order, but the order of those statements does not matter. So we could have it be like that. Okay. And ChatGPT made up this fake data set, and then they have their response variable and their grouping variable. But in our case, what is our data set name? Monty Hall, yeah. And then our response variable was times 1, yeah. And then what was our grouping variable? Decision. So we still had to do a little bit of work ourselves. I know with like I prefer to program in R myself rather than SAS, so I know it's pretty good about 2. Like if you say like, thanks, rewrite code of the data set name be Monty Hall and the response variable be times 1. Let's see how it does that. I think it usually does pretty well in R when I say things like that. Maybe not. No, you don't need to remake the data. Yeah, that doesn't look good. Maybe it tripped itself up now. Well, I got that part right. Yeah, okay. It did it. I think the data set made up here that I think this part might be wrong now, but this part is what. So yeah, it's pretty good at even like making it more specific. Okay. So we run our code, and then here's the Wilcoxon rank sum test results. So the NPAR one way is for, like the NPAR is for non-parametric. That's what that part stands for, because this is a non-parametric test. So there's actually a lot of non-parametric tests you can run with proc NPAR one way. And I believe it's called one way because there is one grouping variable or one explanatory variable. Whereas like two-way ANOVA is called two-way ANOVA because there's 2 explanatory variables. Okay. So here, yeah, it gives you a lot of extra statistics. Mostly, let's see what we were. And obtain confidence intervals for the median difference. Oh, we didn't do that yet. Okay. So to get the confidence intervals for the median difference, yeah, we could ask ChatGPT again, but you add this HL option here, which stands for Hodges-Lehman, which is the name of the people credited with coming up with confidence intervals for the median difference. Here. And so we add that, it'll add confidence intervals to the output as well. Okay. So looking at the results, what are our conclusions? Yeah. Okay. So we have the Wilcoxon 2 sample test right here. Okay, gives all these p-values. This is the 2-tailed p-value, which is what we're using here. We're doing a 2-tailed test. So this says like PR greater than the absolute value of Z. And then there's 2 different versions of the test they give. They give it with they call it a Z. There's essentially, yeah, slight differences in how you can formulate the test statistic I think in general, in my opinion, it's best to use this t approximation one. So we're doing a two-tailed test and we're going to look at the t approximation p-value. So this is our p-value. For testing the median difference. Oh, and maybe we'll give the hypotheses as well. Okay. So we'll throw the p-value down here for now, but okay, so that as a reminder, that's where we got that p-value right there. And looking at the hypotheses, yeah, we can again just copy it from the guide for Stat 216 document and pretty much tweak it to this problem. Where M1 is the median, and then we just replace this part just like before. So median number of times 1 out of 10 for, what was group 1 again? Staying. And M2 is the median number of times 1 out of 10 for switching. So that's how we can get the hypotheses for the Wilcoxon-Frank-Stum test. Okay, so we have our p-value, and then just like the t-test, ANOVA, other hypothesis tests and statistics, we make the decision in the same way. So our decision here is to reject HO, right? And then our conclusion, again, similar to always, when you reject HO, you give the alternative hypothesis in words. So we would say, again, assuming assumptions, if assumptions had been met. Which wasn't the case here, but we would say, and it's actually, like literally we can take the interpretation we gave before. It's going to be verbatim the same, except what do we have to change for this test? Yeah, we just say median instead of average, and the interpretation's otherwise exactly the same. So also why we're not spending a ton of time on the Wilcoxon-Rank-Sum test, because it's so similar to the t-test. You just say median pretty much instead of mean or average. And the assumptions are a little different, but the process, the whole thing is quite similar. So what does the confidence interval tell us? Okay, so for 2E, that was 2D. that was 2D. Yeah. Now we're on 2E. Okay, so for the confidence interval, let's get the limits. All right, the lower and upper bound. You have to scroll to the bottom here. And just gives it to us like this, 2 and 5. Huh. That makes it positive for us. Switch minus stay. Is that the order of the groups? Yeah, they flipped the order of the groups. Interesting. Okay, so apparently the SAS developers with this test decided to make it easier for us and make it positive and tell us the order of the subtraction. So that's kind of nice, I guess. But we have to be careful of it because then it's not the same as the t-test where it'll be negative and the order of the subtraction is different. But so here, okay, so it's the confidence interval is 2 to 5, and it says it did switch minus stay. So let's give like a blueprint interpretation for the confidence interval in the guide document here. Okay. Let's copy that. Yeah, I put the negatives here to try and help with like it undoing the negative if there's negative bounds, but because they flipped the groups for us, now we have to now we have to be careful. That's what I was saying. It's a little bit trickier now, but the big thing is to be careful about which group you're saying is higher. And making sure that aligns with the output. Okay, so we were 95% confident that the median difference in the number of times 1 out of 10 between switching and staying. Okay. So yeah, which one's group 1 and which one's group 2 is not matching here because the SAS flipped the order of which one was group 1 and group 2 and then subtraction here for us. So we have to be a little careful with that. But that's how we can interpret that. Any questions about that? Yeah. Oh yeah. This HL. Yeah, I added that on the last click. Anybody else have any code issues? Yeah. Anybody else have any code questions? Okay, cool. Then, okay. So we ran these two tests that were not valid, but they both suggested that switching is better, right? I mentioned at the start of the activity that actually, if you really wanted to explore this question, you should be using a z-test of proportions, where you have like the proportion of time people won that you're comparing across the two decisions. So we don't do z-tests of proportions in this class, but we can use proc freak just to get some summary statistics about like the proportion of time that we win, right? So yeah, let's do proc freak part 3A. Okay. So we say proc freak data equals Monty Hall. And then it's sort of analogous to saying var and then the variable you want, but for proc freak, we use the tables statement. And so we want, wait a second. I don't think we want to use proc freak here, actually. No, I don't even think that's, I don't know why I wrote that in the activity. That's not what we want to do here. No, that's not meaningful. Okay. Scrap this last part of the activity. We're not going to use proc freak. I think actually what makes sense is to look at the proc means that we looked at earlier. Like that gives us the average number of times. So yeah, we're scrapping this. So I'll get rid of that. Okay. Actually, proc means that we ran earlier, that gives us the proportion of times that people won. A little bit strange. Typically, you wouldn't expect to get a proportion from proc means, but essentially, because this is the number of times 1 out of 10 on average, we can tell from this that the so what percent of the time did people win when staying? We have to do a little bit of a conversion here, but wait, what'd you say? Yeah, how did you get 23? Oh, okay. Right. So, okay. So yeah, maybe breaking this down into like steps here. So each person played 10 times out of 10. So like, let's say for one person, if somebody won twice out of 10, what percent of the time did they win? 20%, right? And so this is averaged across everybody. And so we can think like this out of 10. So then what does this tell us for 30%? So people won 30% of the time. And when switching, people won how often? Yeah, 64.3% of the time. And so if we remember back to Kevin and Captain Holt was saying it's 50-50. And Kevin was saying it's 1/3 and 2/3 chance. So Kevin seemed like he was right? And why is this the case? Why is it not 50-50? It definitely seems like it should be 50-50. I think the best way I've reasoned through it, or that someone else explained, like Kevin explains in the video, is that your decision, one way to view it is to think about when you first start, okay, and you pick a door randomly, okay, without considering that the goat shows up. What's the chance of the door I selected being the winner right at the start? 33%. It's 1/3, right? So that's 1/3. And the thing is, the host always shows a goat because there's at least one goat to show. They always show a goat no matter what you picked at the start. So that actually doesn't change the fact that your initial selection had a 1/3 chance of winning, because you'll always be shown a goat. Like, doesn't depend on your selection actually. And so because of that, you're shown the goat. This one still has a 1/3 chance of winning. And now that must mean, because this is the only other option, the other one has a 2/3 chance of winning. So that's why it's 1/3 and 2/3, not 50-50. And you can reason through it, or you can do, 1,000 simulations and see that, it does end up being 1/3 and 2/3. Right? Great part about computers, because yeah, you can sit here and do the proof or simulate it a million times. That's good enough to get a pretty confident answer. Okay. So yeah, so make sure to turn in that SAS activity on Blackboard. And yeah, that was it for the activity on the Wilcoxon rank sum test. And I'll post this video to Blackboard as well.
Was that